everybody, this is BKC in the game From the Depths, and today what I want to go over about is essentially engine design and power delivery and stuff like that. We have all these ships and planes and boats and we want them to do battle, and without power none of them can do anything. Okay, so we need power, and just like in From the Depths, just like real life, there's no such thing as free power. Okay, you need to either spend some money to get cheap power, and I'll get into that in a minute. But when you get into the game, you have a choice between electric, and the only way to really charge electric, you need a steam engine or you need a fuel engine. You need you need power to charge your batteries so you can actually have electric. So in my opinion, electric would be the king system in this game if the RTGs wasn't our only source of power. What an RTG does is it gives us a little bit of power continuously forever at zero cost, just the cost of manufacturing the RTG. But outside of that, you would need a steam engine or a fuel engine. So essentially, when you get down to it, there's really only two types of power: steam or fuel. Okay, and which one would you want to use in the game? Depending on, I love the steam engines for if I'm building a big, like say it's like a supply ship or something like that, and man, I want it to look really scale and I want it to look really realistic. I want to more for looks than anything. I love the way the steam engines look. I love the fact that when you place them down, you place one of these engines down, there's nothing moving. All you hear is just a whine coming from it, and the only animation is pretty much the smoke coming out the exhaust. So scale definitely has the steam definitely has the cool factor. But when we're talking about efficiency, or there's many types of efficiency. There's cost efficiency, and I think steam beats out fuel in just a tiny bit cost efficiency. There's a complexity efficiency, and I think steam beats out fuel in the complexity department, because a steam engine takes materials directly and burns them, whereas a fuel engine adds complexity to the process. To get power from a fuel engine, we need to manufacture a fuel, and that adds complexity, and it adds expense, and it adds logistics to the game that is not seen with steam. So steam, I don't want to sound like I'm just dumping on steam, because I really do like it, and it really does have some good advantages. But then when you get down to in-game and actual efficiency, I haven't really researched power density, but fuel efficiency and fuel, I would say cost, steam is better because you don't have to have a refinery, and the refinery cost is what makes steam beat out fuel in cost of resources, and putting resources into building the stuff. The same components for fuel engines, I think the steam components cost about the same. What you would use in plumbing up your exhaust on your engine, you could use in plumbing up on your steam, and I think steam's actually easier to build in a smaller space and looks cooler and all that stuff. But when you get down to the two, it's like, okay, well, you have to have, when you start the game, you have a starting forest, and it has a refinery in it. So you say, oh, it doesn't really add much complexity, and I don't mind. So Rich, I want to use what actually is the most efficient, and what I'm gonna argue is that the efficiency of fuel is superior almost in every way, in my opinion. And here's my argument. Let's say I build a 1,000 horsepower steam engine over here, and I set the boiler, and forgive me, I'm not expert on steam. I'm still working. I don't think I've built the actual steam engine in a craft. I built them to play with them, but I never built them in a craft. Let's say you build a 1,000 horsepower steam engine over here, and I set the boiler to burn 1 material per second. Now, honestly, I don't know if that's good or that's bad. Okay, but over here I build a 1,000 horsepower. I don't think I have a 1,000 horsepower motor anywhere. No, I don't. I don't think I do. I don't think this. Oh, I'm stuck. Hold on, I'm stuck. This is something that's been happening in the game. Dang it! Where's my view? There we go. Been happening in the game. I've been getting stuck on things more. They changed the way the magnetic boots hook onto stuff, and I've been getting me stuck a lot more. But anyway, if I was to compare this 1,000 horsepower steam engine burning 1 fuel a second, I mean 1 material a second, versus a 1,000 horsepower fuel engine burning 1 fuel a second, I can't compare the efficiency directly. Okay, I can't say, well, 1 fuel equals 1 material, because it doesn't. But to compare the efficiency to the two, I have to go to my refinery, and the more efficient the if this is burning 1 fuel a second, this is burning 1 material a second. If I didn't need the refinery, if I can convert materials to fuel 1-to-1 without the refinery, then they would be directly comparable. But you can't do that without the refinery, which the refinery adds cost and complexity, because you can't, this thing, the higher above sea level it gets, the less efficient it is at making fuel, and you have to keep it protected, and it's explosive, and you know, there's cost to it. And then once you have a fuel engine, you have to go back and get fuel, where you have to keep materials on your ship to repair your ship, plus you have to keep fuel on your thing to run your engine. So if it was a direct 1-to-1 conversion rate, steam would beat out fuel. But if we wanted to compare the efficiencies to the two, we have to go to a refinery. And a refinery is basically taking material and turning it into fuel. So if it was 1-to-1, we can directly compare. And this is the most basic. Oops, I fell off. I'll probably cut that out. The most basic fuel refinery you can have is the steel, and I think if you put down 1 stack, it eventually builds up dangerous gas percentage that gets too high and it blows up. I think 2 actually keeps it safe, but I think 3 is actually better. And let's go into the thing and see what it says. Right here it says, for every unit of material processed, 10 fuel is created. 10 units of material is used every batch. This can't, you can't change this, meaning that it has to use 10 material per batch, and it's creating 10 units of fuel. So guess what? It is creating 10 units fuel for 10 units of, so 1,000 horsepower over here, unit burning 10 material, a fuel engine over here burning 1 unit of fuel is actually 1 material. So directly comparing the two, the steam engine the fuel engines lose out, because we need the extra cost of this. Even if the densities of the engines were the same and the material cost of manufacturing the engines are the same, the extra complexity added by the steam engine is what makes steam edge out fuel engines. But this is not the most efficient system here. I think if you add corkers and crackers and desalters, it gets more efficient, but the more fuel it creates, the more gases build up, and the more stacks you need. And then the refinery can only use, I think, 100 100 or 101 parts. So 100 parts on top of the steel is all you can do. So the more corkers and crackers you put, the more efficient it gets, but it builds up dangerous gas faster, so you need more stacks. So you run into a limit where you put a corker and cracker, you put as many stacks as you need to keep it from blowing up, and then you put a cracker and you put as many more stacks as you need to keep it from blowing up, and basically you end up with maximum efficiency, I think, is at 10 corkers and 10 crackers, a desalter, this, and I forget how many it is. I think it's something like 50 or 45 exhaust stacks, and that gives you your maximum efficiency to where if you put a stacking an extra desalter does nothing. Put an extra corker or an extra cracker on actually makes it less efficient. And I think maximum efficiency, I think I got it written down here, is a fuel batch of 2,460 for 10 materials. That makes processing materials into fuel 246% more efficient than burning them directly. So in that situation, if I have a maximum efficiency refinery, and I go back to the same scenario, a 1,000 horsepower engine that burns 1 fuel a second, and 1,000 horsepower steam engine that burns 1 material a second, you compare the efficiencies, and you have to minus out a little bit because of the cost of the refinery, and then how much is your time worth with the logistics of managing all this stuff. But it's still in the range of the 240% more efficient. Okay, so this is the reason why I mostly use fuel engines. And then when it comes into using direct power of the engine directly versus putting the power into battery banks, we'll get into that into the electrics tutorial. But today we're going to go over just the fuel engine, the parts, and basic design philosophy, because we've already established that for 1,000 horsepower, 1 unit of each, you got to go to the refinery to directly compare the two. And if I can get, now I don't know the numbers exactly, but I don't know how much power you can actually make on how much units of direct steam power, but I keep hearing that it's 55 times more efficient to make fuel. But on my one-to-one scenario here, on a basic refinery, steam wins, but then if I max out the efficiency of my refinery, fuel is about 240% more efficient. So to me, the clear choice is fuel engines. Essentially just from the fact that material is what you need to build ships, and instead of burning the material, it's essentially like taking a larger ship, and if you run out of material, you can pirate one of your smaller ships to put it into the boilers of your smaller ship. So you're actually eating ships to power your thing. And you say, well, I'm not actually eating my ship, but you're eating the material that could be used into another ship, which means more firepower, which means you can win more battles, and you could take all your smaller ships and put them into a bigger ship and get more firepower, and it's just more power, and that's what your game is about defeating your enemy. And if you can get more power and with more guns and more everything, then you can defeat your enemies quicker. And that's what actually happens in the campaign. Once you kind of beat the Deepwater Guard, you become so powerful that sometimes you go to other factions and you're like, wow, that faction I thought would be more scary, but actually you've grown in your building, and you're dispatching with your enemies faster than the tech level of the enemies rise. So fuel engines to me is the clear choice. And this is the basic parts. We'll go over the basic parts and then we'll finish this video out with a basic design theory. This is the fuel generator. It says the master block large fuel guzzling engines, and it generates energy. This is what generates the power so you can charge your batteries. I don't think it does anything on its own. I think if you put a cylinder directly in front of it, it makes 10 horsepower. Now, to me, you say, oh, well, 10 horsepower, you throw a whole bunch of these down, and you throw a whole bunch of cylinders down, and it makes, 10 of these down, you can make 100 horsepower. But 100 horsepower, what can you actually do with 10 horsepower? I think a ammo processor actually uses 10 horsepower. So if you just wanted to put a block of wood floating in the middle of the ocean that creates, that generates ammo for you, then put an engine block on it with a cylinder, but I don't see any actual usefulness in the game. So, but every engine needs this piece, at least one. You can put as many as you want, but at least one. Okay, the advantages of this block is it allows you to manufacture an engine as big as you want and as small as you want. The disadvantage to this block is that if you don't have one, you can't make any power. And another disadvantage of this block is when you're talking about density, no matter what, you're actually, out of all these motors, that's one block that makes 0 power, and it kind of hurts your density. So that's the bad thing about this motor, this block. But without it, you can't have, thousands upon thousands of horsepower. And you could put a cylinder directly on the front of it if you just needed a small motor. You wouldn't necessarily. Well, you could probably make about, I would say you can make about 750 horsepower with just a block and a cylinder, and then just throwing a whole bunch of these parts together in certain situations. But I think 750 is about the limit, I think, what you can make on a single cylinder without getting stupid crazy. Actually, I think it's a hard limit. I don't think any combination of these parts can get more than 800 horsepower out of a cylinder. I think it starts getting so inefficient it actually kind of caps out about 780, somewhere right around there. And there's a point of diminishing return where to get the actual 800 out, you need so much room that you could actually, in the same amount of room, you can put 2400 horsepower. So it kind of becomes irrelevant. But the crankshaft, if you just want to put one cylinder and get it, in between 100 and 750 horsepower, you don't need a crankshaft. But if you wanted to put multiple cylinders, you need a crankshaft. And now the disadvantage of a crankshaft, it's just like the fuel block. You don't necessarily need it, but if you want more than one cylinder, you need one. So if you want to get into multi-cylinder engines, you need one. The disadvantage of the block is that it makes no power, so it burns up some of your density. The crankshaft in here uses probably about 8 or 9 blocks that is burning up some of my engine density and not giving me anything in return. What it is giving me is the ability to chain whatever power my cylinders make into a single engine and add together all the power. You technically could get 800, 1000, 2400 horsepower without crankshafts by putting a single cylinder on a block, getting your 100 to 750 horsepower, then lining up multiple engines and just adding together without cranks. And the advantage to that would be it would cost more because you would be adding more engine blocks, which is the most expensive piece on an engine. So your cost would go up, but your power would be the same by having a whole bunch of small single cylinder engines adding up to 2400 horsepower versus an engine like this making 2400 horsepower. And the advantage of a whole bunch of small engines would be Not so much the density, because individually their density would be pretty good, but all of them added together, the density would be terrible. But the redundancy would go up. Okay, the redundancy of a whole bunch of small engines. You have this one on the back corner, left corner of your craft. You have one in the back middle of your craft. You have one on the right corner, back corner of your craft. You put one in the middle and the right of your craft. You build one on, and you spread them out in your ship. Then none of them being taken out would be a significant loss in power. If you had 24 of them all creating 100 horsepower, if you lost one, you'd only lose 100 horsepower. So you don't necessarily need a crank, but if you want to just put one of these down cost-wise, a crank actually does some good. You can utilize them. It lets you add power together, or cylinders, without having to have a massive room full of a whole bunch of little generators. So it can get your density up without having to have a whole bunch of small generators, small motors. The cylinder is your power, essentially. This is the block that gives you power, and putting it on a thing gives you 10 power. Adding a carburetor or an injector gives you, a carburetor gives you 100 horsepower, and if you put 2 carburetors on, you get 200 horsepower at twice the fuel use. You put 3 carburetors on, you get 300 horsepower at 3 times the fuel use, and 4 carburetors on gives you 400 horsepower at 4 times the fuel use. Now, you say, okay, well, so the theoretical limit of a single cylinder with a carburetor should be 500, because one side needs to correct to the crank or the block, but that engine wouldn't run. What would happen is you would be getting 500 horsepower out of it, and there would be no exhaust. So, and it'd be burning so much fuel per single cylinder that it would almost overheat instantly. So you need to have something to get the exhaust, the heat out, and so the best way to do that is you need an exhaust. So the hard limit on a single cylinder with a carburetor is roughly 400 horsepower per cylinder, because you have to have an exhaust. So there's 4 sides. An exhaust on the 5th side gives you 400 horsepower. Okay, that is pretty much the hard limit per cylinder. And then an ejector, you can have 4 of those. Now they give you 200 horsepower per injector, and if you go by the same logic, you would say, okay, well, I could put 4 of these and an exhaust, and I can get 800 horsepower. Okay, but in reality, you can't really get 800 horsepower because of something that happens between carburetors and injectors. Injectors give you twice of power per block on a cylinder as what carburetors do, but I don't remember what the actual fuel usage is. I think they're like 3 point something times the fuel usage. They draw a lot of fuel, and then from the depths, the mechanics of the fuel engines, the more fuel you burn, the hotter the motor gets. Okay, the hotter the motor it gets, the less efficient it gets, and so in theory, putting 4 of these on a single cylinder motor can give me an 800 horsepower motor, but you're not going to get 800 horsepower. You're going to get about, I think you could max it out around about 780. You might even be able to push it into about 790 horsepower, but you're not going to get the efficiency 100%. There's a law of diminishing returns there, and so but the theoretical cap I would say on injectors per cylinder is about 750. Okay, and then we have here's your exhaust. I'll get to that in a second. This is your adapter, and what a crankshaft adapter does is you can put that on side or on top of a crankshaft, and you can extend it out in one direction per. I think you could put it on side, and you could get you can get a cylinder on top and bottom, but you can't put a cylinder. I don't think you can on the side. But you can extend out a crankshaft and get two more, and that lets you really all this part does is again, it's like a crankshaft. It hurts your density of your engine because it doesn't make any power, but it lets you make more power by putting more cylinders in more efficient layouts. So that's the benefit and advantage of that block. And then your exhaust, to me, is probably the most underrated parts of an engine because of the way the mechanics work. The more fuel you use, the more heat you generate. The more exhaust you have, the more heat you remove. So the advantage of an exhaust is it hurts your density in the fact that it makes zero power by just shoving it on a cylinder, but it pays you back in the fact that it cools your cylinders at the cost of one block. Okay, so if they keep your cylinders cool, they make more power. So they don't give you power directly. What they do is they keep you from losing power. So the exhaust is one of the most underrated blocks in my opinion, and I see a lot of people online building engines and they not taking advantage of the power of the exhaust. Okay, so we have the two the carburetor versus the injector debate, and I would say the carburetor is more efficient. And then we have what I call the efficiency parts. Okay, we have the supercharger. Okay, and I think, if I'm not mistaken, I think putting a supercharger on a carburetor, so say this draws one fuel, let's say we're making any particular engine and this thing's drawing one fuel a second. Okay, I think a carburetor is a 30% fuel efficiency boost by just putting it on, and it's a single block and it's a 30%, and that 30% is what I think is reverse proportional, I think is what it's called, meaning at a 1% load on your engine, this is giving you 100% of the efficiency boost. And when you get down to the 100% load, it's only giving you around a 3% efficiency boost. So overall, it's the lowest efficiency boost out of any part of the efficiency parts. But if you had an engine burning one fuel a second and you divide that by 1.3 to get how much fuel it would burn by putting a supercharger on it, that would be 0.7. With a rounding, it would be about 0.77 fuel a second, which would round probably up to 0.8. So you would get a fuel that was burning every fuel you burn a second by having a supercharger on every carburetor on your engine. It would knock you down to about 0.8. So it would, I know you say, oh, well, 30% of one fuel a second should knock you down to 0.7, but that's not how the math works. It's actually 0.8. So, and then as the load on your motor rises, usually the fuel consumption rises. This has less efficiency the more the load rises. So it actually is the most efficient at idle and the least efficiency at 100% load. And it has a benefit that it's a single block and it's very easy to use. And so if you want a small motor and you want to try to, you're okay with, like, say 1 fuel consumption a second or 10 fuel consumption a second, Matter of fact, the more fuel the engine uses, throwing a supercharger on it gives you the biggest benefit for a single block. And that's the advantage of a supercharger. I think it's 30% efficiency boost for a single block. Now, turbos are 2 blocks, and if you get into this inline, they become 3 and 4. 3 and 4 blocks to actually add one. But the same could be said about this. They're both 2 blocks, and they don't add anything to power. Which in real life they kind of would. They would affect your power curve, just like the supercharger. But they take space, and they actually get pretty complex with plumbing them up, and I'll get into that in another tutorial. But there's the inline. Now that's an adjective. Remember, inline is an adjective. It's not a descriptor of how it's being used, and that's something I'll go into on the turbo tutorial. That this is just explaining the type of supercharger. It's not explaining how it's being used. And then this is just a turbocharger, because at one point in the game this is all we had, and this was added in after, so you have to differentiate the two with the term inline, which is an adjective which explains what type of supercharger it is, and it's just explaining that it's different than this one, but it's not explaining the use case. So that's a mistake I see in a lot of people who understand engine design, but they don't transfer the point about that in the video and make people think that, oh, you got to use this because it's more efficient. And they're not. They're the exact same part. They do the exact same thing. And what happens on a turbocharger is the more exhaust gas you feed them, the more efficient they become. So if I put one turbo on one cylinder, I think feeding one exhaust gas to feeding like 1 to 3 exhaust gas into a turbocharger at a 1% load on a single cylinder makes the turbo 26% more efficient. It's less than the supercharger. It's 2 blocks. So you say, oh, well, that's terrible. I don't like that. I don't want that. But the difference is with the turbo, which in my case makes it superior. Yes, it's feeding an exhaust to it only makes it 26% more efficient, where a supercharger is 30%, and this is 1 block, and this is 2 blocks, and this is more complicated to use and needs more blocks to make it actually function. You say, well, man, a supercharger's not good, we don't want that. But what makes a supercharger better and more efficient in my eyes is that the more exhaust we feed it, every exhaust we feed it, it gets slightly more fuel efficient. So at 1 exhaust, I think it's 26% efficient. At 2 exhausts, I think it's like 27.5% efficient. And 3 exhausts, it starts getting more and more and more. Each exhaust we feed it, it becomes a little more efficient, but it's smaller steps than a supercharger. But a supercharger, you can't just put 20 superchargers in a low and then they'd be 300, 10 superchargers in a row and then they're 300%. Superchargers can't be chained like that, but exhausts can, and they can be chained in 2 ways. They can be chained by feeding them more exhaust, which makes them more efficiency, up to a maximum 390, I think it's 393% efficiency, which is 13 times more efficient than a supercharger. Or you can put them in line, and they don't add their efficiency, but if I have 30, and they reach maximum efficiency at 30 exhaust. So to get 30 exhaust out of this, I have to have a cylinder that creates power, so it has to have a injector or a carburetor on it. So I can only have 4 carburetors per cylinder or 4 injectors per cylinder, and that's going to be, you know, between 400 and 750 horsepower, and it's going to be extremely inefficient. But if I put a turbo, since I'm using a lot of, I mean, if I put a supercharger, because I'm using a lot of fuel, I get an instant 30% off the top, which drops every fuel consumption down to 0.8. If I put a turbo, I need 30 exhaust. Well, I'd have to have 30 cylinders to get 30 exhaust to this thing, or give up some of my power per cylinder by removing carbs to collect more exhaust to put into more turbo. But then by doing that, I can actually boost my efficiency of putting a single carburetor on this thing, collecting all 4 exhausts on multiple cylinders. Yes, I'm only going to be getting 100 horsepower per cylinder, but I can take probably like a 10 fuel usage per cylinder, and by putting all the exhaust into a turbocharger, at least 1 turbocharger per carburetor, I can gain 12 times efficiency boost over a supercharger. And that there's no difference between the two. Inlines are sometimes more efficient, easier to plumb up and become efficient, slightly more efficient in that way. But we're talking about material cost wise, and material cost on exhaust pipe is 1/4 of a material per exhaust pipe. So if you can, material wise, a ship like this, probably a big engine like this, probably only has about 5 to 7 material worth of plumbing on it. So plumbing wise, I wouldn't really worry about the cost difference between the two. It's just that this one can usually plumb up exhaust a little more efficiently than this. There is some use cases where you can plumb up this more effectively than this, but the difference between the two, for all intensive purposes, are identical. And the difference between a supercharger and a turbocharger, if you enter small space and you just want a quick efficiency boost, a supercharger wins, and a turbocharger in larger engines and more powerful designs, turbos, win out. And then there's another use case, is if you want a motor that, let's say I have a 1,000 horsepower motor using superchargers. Well, it's probably going to give me the most efficiency, around 10%. And my argument to a supercharger versus a turbocharger is, if you want to charge your batteries with a 1,000 horsepower motor at idle, you can get the most efficiency and density out of using superchargers, but 1,000 horsepower at a 10% load is only giving you 100 horsepower. I would actually rather throw 1 carburetor on 1 cylinder and then throw 4 turbos on it, use like 1/4 of the fuel, and run this motor at 100% over running a 1,000 horsepower motor at 10% to charge batteries. I'd rather have one motor, a little 3x3 motor using, less fuel because of the amount of turbos attached, versus a 3x3 engine with superchargers attached. Just my opinion. And then if you start adding 4 carburetors and 4 superchargers, you're still using 4 times the fuel, whereas 4 turbos can almost reduce your fuel by almost 4 times. So you can have a single cylinder with 100 horsepower, reducing your fuel consumption by 4 times, or you could put more carburetors in and increase your fuel consumption by 4 times, and in the same space. And if you want to try to reduce it with turbos, then the motor gets super huge and there's no point. And then at that point, if you're trying to make 400 horsepower out of a single cylinder, you're probably better, and you don't care about fuel usage, you're probably better off with a injector. So that's the basic parts. And once again, when you get back this thing, to be honest, I'm not gonna. I like it for scale reasons, and when it first came out, I started using them. I really love the big generator stuck on the front of a motor like this, a big motor like this. I think it looks fantastic. But if you look at the part description, let's go into build mode. And then we'll force over that and we'll hit E. The radiator, it says the radiator helps keep the engine operating at a lower temperature. It costs a bit of efficiency to run. Now, here's the logic loop that I see a lot of people getting stuck in. Okay, they want all the power. They want as much power out of a single cylinder as they could. Well, that's an injector. Well, that burns a lot of fuel. Okay, and you get your 750 horsepower out of this thing, and you're burning a crap ton of fuel, so it instantaneously overheats. So then you say, well, I'm going to put a whole bunch of radiators on there, which actually makes the motor run cooler, which helps efficiency, but it uses power to cool, so the power that it gains you back, it wastes in the power. Now, I have no way to test how much power this uses versus how much power it saves, but if it uses power to save you power, then it's a zero-sum game. And if it uses space for a zero-sum game, then it's all negative. Okay, I don't see the point of this block. I don't know why people use it so much. I'll show you in future tutorials that it actually hurts you more than it helps you. And all my motors, none of them use radiators. I don't know. I don't use injectors very often. I use superchargers if there's space for them that otherwise couldn't be occupied by a turbo. But I use engine blocks because I have to, crankshafts when I need to, adapters when it makes the engine more powerful or more efficient, and cylinders, of course, because you need to make power. Carburetors almost always over injectors. I use turbos almost always over superchargers unless there's a block open above the carburetor that I can't otherwise put a supercharger, and I never, ever, ever, ever use radiators. So that's the parts. And the last part of this video before I close it out, I want to talk about design, engine design. And I'm not going to tell you how to build a motor, not in this tutorial, or why you want, or what's the best in your particular use case. I'm going to talk about design in general. And what we have in design, and this is true about like physical products. Physical products, I'm talking like your cell phone, I'm talking like your car, I'm talking like your television set, your computer, your physical properties, physical products in real life. Because this relates, and this is where I actually learned about this, and it translates into from the depths. Not because this is a real product, but we're talking about virtual material, we're talking about virtual fuel, and we're talking about virtual space. But if you get rid of the virtual and you compare it to real life, this applies to real life across almost every single thing in life, physical, product-wise, that somebody manufactures. It's in real life, and you can find it across many different things. Things can be broken down into three basic functions. Okay, first is going to be the cost. Everything has a cost. Okay, and by cost, I don't mean, you know, how many dollars, because something that's cheaper that does the same thing is going to be more efficient, have more value. And so cost can be value in material that goes into it, cost as in time. If you had a hammer and you could build a house, you can build a shed in a day, versus taking a rock, but it takes you 2 days to, beating the nails with a rock. It would take you 2 days to build a shed. Well, the rock is cheaper, but it costs you time. So cost can be either material, or it could be time, or it basically it boils down to that. Okay, then you have and cost can also be broken down into efficiency. Cost can, if two motors make the same power and one drinks half the fuel, then the first one the more efficient one costs you less money. So we're going to bring that into efficiency. And from the depths where it relates to engines, we're talking about efficiency. Okay. Then we got, for any given amount of fuel, one engine makes 100. This is where it gets into the carburetor and the injector. Okay, if you don't care about fuel consumption, if you don't look at the fuel consumption, you put on a blindfold and you don't care about fuel consumption, well, the injector is better because it makes more power. And that's another side of the puzzle, piece of the puzzle, is power. And power can be related into, like I said, when it talks about, you talk about like your computer and your cell phone. Your computer draws power from the wall, and you're like, okay, well, I'm playing a game. Who cares whether it draws 100 power or it draws 1,000 power? I'm still playing my game. But it relates more. It has to do with performance also. That if two computers are drawing 500 watts of power out the wall, and one can play a game at 30 frames a second, and the other one can play a game at 60 frames a second, the one that playing the game at 60 frames a second is more powerful because you're getting more performance out of it for the same amount of power going in. So power can be both actual power and performance. Okay, so that's another piece of the puzzle. And then when we're talking about the last piece of the puzzle would be from the depths would be your density of your engine. And what density actually refers to, density is usually calculated, and from the depths you take your 4 by 5 by 7 box that this engine fits in, and you take you multiply that 4 times 5 times 7, and that's 140 blocks. 140 blocks of material gives me 1,200 horsepower. So the density of this motor becomes 1,200 divided by 140, and that gives me a 8.57 density. Okay, now what density is actually referring to is going to be your quality of your motor. Okay, I can come over here to one of the worst engines density wise. This motor right here makes 200 horsepower in a 4x4x7 binding box, and its density is 1.79, and it's not very efficient. I mean, it's good efficiency, but it's not efficient space use. So it's not a good quality. So it would be space use, and quality would be density. Now, since the way most people from the depths and the community and designs, they compare motors, they talk about the power per block, and that's usually just how many blocks space does it take up divided by the horsepower. So Density is directly related to power. The more power you make, the higher the density. So those two are pretty much intertwined. So you have efficiency, which is cost, power, which is performance, and density, which is quality or space usage. Okay, and you put those in a triangle, and we got what's called the design triangle. Let's put efficiency in the bottom left-hand corner. We'll put power in the bottom right-hand corner, and we'll put density in the top corner. Density is something you would always want to strive from. If you start anywhere inside this triangle, essentially what you can have is you can have an efficient motor, you can have a powerful motor, or you can have a dense motor. Pick two. You can only have two. Okay? If you pick a dense, powerful motor, it's not going to be very fuel efficient. If you pick a dense, efficient motor, it's not going to be very powerful. And if you pick a powerful, efficient motor, it's not going to be very dense. That's kind of the rules from the depths and the things that you have to balance. And you say, well, I can get a fairly average space usage dense motor, and I can get a very average power, and I can get a very average fuel efficiency, and you can combine all the three, but you're going to be sitting dead square in the center of that triangle. Okay, and if you push the density, if you push the line, the point inside the center of the triangle towards density, you're going to lose efficiency and power. And now I'm talking about a perfect design. Most engines are not perfectly designed, and you have to have some kind of trade-off. But if you push toward density, you're going to lose power and efficiency. If you push towards efficiency, you're going to lose density and power. If you push towards power, you're going to lose density and efficiency. Now, since density and power are directly related, the lines between the two, by pushing more towards density, usually power comes with it, and then if you push more toward power, usually density comes with it too. So power and density are linked together, but power and efficiency are not necessarily linked together. As a matter of fact, I would say they buck each other, and then efficiency and density are not related together, and they actually push away from each other. So when it comes to power, if you need power, just design as small of a motor as you can. Just design as small a motor you can, and either work for efficiency or density, depending on whether efficiency you'd work toward if you have the room. Now, efficiency, I guess, would kind of be linked to density in a little bit, in that as a motor becomes more dense, it becomes more powerful, and then I don't think the fuel goes up like a twice as dense motor uses twice as much fuel. I think it gives you just a tiny bit back, but the point is you can have two out of the three. And if you make a powerful dense motor, you walk the line right in between the density. You know, you can go from power all the way to density and have the same efficiency, or you can walk from density to efficiency and have the same power, or you can walk from efficiency to power and end up with the same density, and you're walking the lines of that triangle. Now, you can be anywhere inside the triangle, but if you're at the corner of power, you can either have density, a small space, or you can have efficiency. You can't have both. If you're at the corner of efficiency, the density can be high, but then you don't usually make a lot of power. And then if you're at the efficiency corner and you want a lot of power, it's usually not that dense. If you're at the density corner and you push towards power, it's usually not efficient. And if you push toward efficiency and with a dense motor, usually you lose power. So that's how that works. And there's trade-offs in almost every design, and you have to balance that design to where you're somewhere inside of that triangle, It's just where your motor sits in that triangle. And that's we'll get into for the next episode, because how do you tell where are you at in that triangle? Well, without dynoing your motor and testing your motor and comparing it to other motors and not having a reference point or a comparison point, you are floating around in a engine design triangle and you have no idea where you are at. So that's it for this episode. We went through parts. We went through the difference between kind of like steam, and the efficiency from steam is directly correlated to your refinery. The efficiency between the two, you can't compare them without comparing your refinery in the mix, and at a 1-to-1 ratio, steam beats out, but just adding any other part to a refinery pushes steam. Fuel probably about, I would say, up to 240% more efficient, and I would argue that it's infinitely more efficient. And then we went over the parts, over the goods and the bads of the parts, and when we get into design, we'll see what parts I use and why the parts I use. And then in the next episode, we'll go over the rating system, because we went over the design that we have a power triangle made up efficiency, density, and power, and at each corner one of these things sits, and your engine design is going to be somewhere in the middle of this triangle, and if we push it toward any one corner, we lose on the other two corners. And in the next one, we'll kind of discuss where we sit in that triangle. And I'll see you guys in the next one.